All right, so today we are going to end. Oh, did I forget my pens too? Did I just go? No, I didn't. I didn't get my pens. Let's go back downstairs and not get all those things. So we are going to end a little early today, probably like, I don't know, 2:40-ish, somewhere around there. We'll see. But I wanted to talk to a couple of people had asked about question 2 from your handout worksheet thing. So I was going to kind of look at a similar situation and kind of help walk you through it because it is a little confusing. And before we go there, though, I kind of wanted to just talk about level curves in general. So I found a couple handouts, printouts that I thought were helpful. I like this. I like this because it kind of really helps me kind of see what's going on. If I look at this, this kind of mountain range here, the 2D projection onto this 2-dimensional graph is the level curves. And if you can, it's kind of hard to see. If we zoom in really close, you still can't really see. If we zoom in really close. Oh yeah, there you can. You can see the numbers, right? So literally this curve right here at 1100 is corresponding to this elevation of being 1100. This curve a little inwards at 1200 is corresponding to this higher elevation at 1200 and so on. There's 1300 right there corresponding to this, 1400, right? Probably there-ish corresponding to that and so on. So that's kind of the very bare bones, like what a level curve is really talking about. It's just all of the stuff that's at that same elevation or value in general, right? I should point out, it doesn't have to be literally a map. It can be just something representing values that have some sort of meaning. Question? And then the change in elevation would be evenly spaced out because it's like 100. Well, so typically I would say, so I wouldn't say that the curves are equally spaced out here because they're not, right? If we look down below, right, there definitely isn't equal spacing between them. But what is typically the same change is the amount. So you're right in that we're always going to be picking like the same sort of, at least like for regular maps. Typically we're picking like heights of 1400 feet, 1300 feet, 1200 feet, et cetera, to have a kind of regular spacing. But that doesn't mean that the level curves themselves are equally spaced from each other. Other questions about this kind of drawing here? I will also point out, if you look down here, right? So the closer your level curves are together, the steeper your slope. Whereas the further apart they are from each other, the gentler your slope. Which is kind of actually useful information. If you're ever out like actually hiking in the mountains and you are looking at a topographical map, it is useful to know that this is what this means. Actual real world use. Oh, I should give you guys this reminder to fill out the attendance form when you have some. Let's look at another example, an actual real topographical map of somewhere in Yosemite. Okay, well, that's kind of big. So here's a topographical map. And what I really, really kind of want to point out is, again, the thing I was just saying. If you have, and so looking here, like the big level curves, that one's at 1200. Can you see that? You can see that there. There's 1200 there. I'm trying to look for other numbers here. I don't see exactly how much they are apart from each other because I see a 6400, I see a 6200. It looks like each of these kind of thicker lines, oh, you guys get it, try and over here. And the thicker lines look like they're all 200 feet apart from each other. Right, so from here to here, you're gaining 200 feet in elevation, or losing, depending on which way you're going. And then if you look over here, right here, at the panorama cliff, from kind of like, so, sorry, let me go back over here. So here, if we look from here to here, that's a fair amount of distance to cover. I don't see a scale on this map, so I'm just going to go with it's some amount of distance. And in that amount of distance, you're elevating 200 feet. So if I were to hike from here to here, maybe not too terrible. On the other hand, let's take that over here, from like maybe here to there, that's about the same amount of distance on the map, but I'm going from an elevation of, I think, 4,800 to an elevation of much, much higher, because I'm crossing so many level curves, right? 5,000, 5,200, 5,400, I don't know, probably like 6,400-ish. That's probably what's over there. It's much steeper because you're crossing a lot of level curves at once. You were going up and up and up and up and up in the same amount of distance, whereas over here, you didn't cross nearly as many level curves in that same amount of distance. So the more level curves you're crossing, the steeper your path is, or the more change there is along your path. On the other hand, if you travel along a level curve, like I said, I was going to hike along this level curve here, I'm not changing my elevation at all. I'm just having a nice, fairly easy, breezy walk through the national forest. So along level curves, you don't change your elevation or the value of your function. Crossing level curves is how you really increase or decrease the value of your function. Let's see, I think I had one more. I feel like those ones are not so important. This one's not so important as well. Yeah. Yeah, cool. So let's look at the examples I actually have to work on. So I've got a handout. Practice ahead of time. So here you guys go. You can also, if you're in the meeting, another one, I've got plenty and they want a copy. You want a second copy, you can grab one. Okay. Maybe. Perfect. Okay, exactly enough. How unlikely was that? Okay, so this topographical map that I found by Googling level curve map, whatever, is a map that is displaying EM31 conductivity as a function of where we are on this grid. So just taking a look at a couple things, I can see in here, right along this level curve, the conductivity is 8.0. I don't know what the units are. We don't really care. I guess I actually don't really know. I don't know what the MS is. I didn't look at the units. I wasn't paying too much attention. It's not that big a deal. Not for at least this problem. And here we have kind of what I would say is the lowest amount of conductivity. And if I move, over in this direction here, my conductivity is 8.5. Along this curve, it's 9, 9.5, 10, etc. So let's ask ourselves some questions. And I wrote some questions down here. And I'm going to need to go back and forth between paper. So, come on, paper. Here's our first question. And we'll go back and forth. So question 1. What is the approximate level of conductivity at the XY coordinates? I'm going to write down here, -31, -30. By the way, in case it wasn't clear, I will just state these questions are meant to mimic the questions that are on question 2 of your worksheet. So these are very similar questions. The question 2 is asking you just a different graph and different numbers. Okay, so looking back over here. Oh yeah, sure. So what is the approximate level of conductivity at XY, -31, -30? Or in other words, what is the approximate value of F of -31, -30? Right, thank you. Cool. So looking back at our graph, we're going to go to those coordinates. We're going to say, okay, X is -30. Oh, I have to use a ruler. I love this. So jazzed about this ruler. So I go to -31, which is right there. Look at that. So I'm going to go like, and -30, which is right there on the y-axis. And looking there, those 2 points cross almost exactly on the level curve 10.5. So I can say, great, I'm pretty sure that F of -3130 is approximately, or -31 -30 is approximately 10.5. So whenever you're being asked to find an approximate value of a function at a point given its map of level curves. You're just being asked to find what curve are you closest to and what is the value on that curve. Okay. So now it gets a little more interesting. What if, frame very easily. My next question here. If we move slightly north, how will the conductivity change? Or in other words, how will the function change? Function value change. Okay, so let me raise this up a little bit. All right, so I should say if we move slightly north from that point, I think that was implied, but right, just slightly north from the point -31, -30. In case that wasn't immediately clear. So if we look at that point, so if I there and I move slightly northwards, are my level curve values getting bigger or smaller? Definitely smaller. So we would say we're decreasing. The conductivity is decreasing in that direction. Conductivity, aka function value, is decreasing in that direction. And what's typically true, although not always 100% of the time true, is that if you move in the opposite direction of something, then the opposite thing is happening. So if I were to instead move in the southward direction, well, actually, so it's not 100% true here. So, right, like if you move in the southward direction, you're actually kind of going back towards that same value. So you might dip a little bit, or you might actually, sorry, you might increase a little bit because you're going a little bit bigger than 10.5. So you're kind of increasing a tiny bit as you move this way, and then you're decreasing again back to 10.5, and then decreasing even more. So a lot of the times it's true that in the immediate vicinity, if you move in the opposite direction, the opposite thing happens. But if you move too far, then definitely also, if you have questions along the way, you're welcome to ask them. All right, let's ask ourselves the kind of corresponding question. What happens instead if we move? What about moving slightly to the east? Okay, well, again, looking at this point here, if I start moving eastward, so I have to kind of look towards what's my next level curve. If I move eastward, I'm moving towards a level curve that has a higher value, right? I'm starting at 10.5 and I'm moving towards 11. So I would be thinking that I'm definitely increasing my value here. So the conductivity should be increasing. I'm just going to write a question mark there. I don't need a question mark. It's just a statement. Now, a question that you aren't being asked yet, but I think is definitely something you're going to get asked in the future is, from this point, which direction would I need to move in? Or I should say, not which direction, because I don't want to be like north by northeast by north, right? Like I don't want all that. What direction would I draw to be increasing the fastest? So if I want to climb this, or if I want to increase my conductivity as quickly as possible, which way should I be going? Should I be going up and to the left, up and to the right, down to the right, just right, down, right? So which way looks like I'm going to be getting biggest the fastest? Well, I want to head towards the next biggest thing as quickly as possible. Definitely going to the left looks like we're getting smaller. So it looks like I'm going to be going some way to the right, but that's really not bad. Or it looks like I'm going to be, I think I want to go that way. That's the way that would probably, I mean, again, it's an approximation. It's not exactly 100% right, but that is generally the direction I want to go. If I'm trying to increase as quickly as possible, I'm trying to get to kind of the next biggest level curve as quickly as possible. Or another way of saying this, I want to cross level curves perpendicularly. That's how I'm going to increase value or decrease value as quickly as possible. Again, this sort of question is not on this handout, but it's definitely coming in your future. And I'm also just going to say the words because I might as well say them. If you're trying to cross level curves as quickly as possible, that is called the direction of the gradient. The gradient is going to make you increase your function value as quick. I should say the gradient, which is a vector, is the direction that increases the function value as quickly as possible. We'll say it again for sure. Definitely, we're not there yet, probably, but it's definitely coming soon. So yeah. Well, let's ask a few more questions. Like right here. What value of x comma y would lead to the minimal conductivity? Okay, well, let's see. Where on this graph do we have the smallest numbers? Or what is the smallest number you see on this graph? Yeah, my favorite number, 8. So I would say that the minimal conductivity is somewhere in here, right? Because if you're thinking about it, as you go in this direction, right, like from here, you are decreasing. So between 10 and 9.5, between 9.5 and 9, between 9 and 8.5, between 8.5 and 8. And then if you're crossing this direction, you're smaller than 8. So in here, we are smaller than 8. So somewhere there. Now, there's a lot of room in there, right? We can kind of pick it. So I would probably try to get something that's kind of in the middle-ish. I'd probably pick something like about right here and say, okay, the x-coordinate's about -31. The y-coordinate's about -27. It's probably not exactly the right answer, but again, we're just being asked to kind of give an idea. So maybe the answer is a coordinate of x being, I said -31, and y being -27. Maybe, but maybe you want to go a little higher. Maybe you want to be like, if you want to go a little bit over this way, you can say like, I don't know, -31.2, comma, -26.6, right? Maybe that's real, like maybe we're a little higher up and a little further left. It doesn't really matter. The other question, which I feel like is a little harder to answer, is where is the maximal conductivity on the graph? Well, let's take a look. Where are the biggest numbers? Yeah, 11.5, most right and probably down. So let's see. So it looks like every time we cross a new level curve, we're increasing by how much? Or decreasing by how much? Yeah, 0.5. So this would be 11, this would be 11.5, this would be 12. Let's see, this would be 12, 12.5, 13. So it looks like way over here in the corner. That's probably the point where the conductivity is maximal. So I would probably say that my coordinate would be x is for sure -26. And the y coordinate, I'm probably just going to go all the way down to -33. It's not a great question because it's kind of like off the chart or off the graph, but it's still okay to ask. All right. The last thing we want to ask is questions. Oh, we got it. This last question, the last question on this kind of handout thing is definitely the hardest question to answer, in my opinion. So we'll do 2 of these. Let's pretend or suppose that y is fixed at -27, but x can vary. We want to plot conductivity, which is our z thing, versus the x coordinate. Okay. So let me I'm going to grab a new piece of paper. So I got like plenty of them. If anyone needs another one, you're welcome to another one. I made way too many copies. Come and grab them if you want. So I'm going to hold y at, what did I say? Negative 27. My y value is negative 27. I should have brought it. Let's just use the piece of paper. Do that. Yeah. Just going to draw this line to make my life easier. No danger of drawing with paper as you would. Okay. So there's my y equals negative 27. And I mean, I could try to be super duper precise. I don't really want to be super duper precise, but I see that I'm just going to kind of look at the x, or sorry, not the x values. Well, I am going to look at the x values. So I'm going to plot negative 36, negative 4, negative 32 on my x-axis. And my corresponding z values, or function values, or conductivity values, well, I can see, right, this level curve is 10. This is 10.5. So my z values are starting a little bigger than 10.5, and then 10.5, 10, right? I'm just going to try and plot all of these kind of values along the vertical axis. This is where I feel like you can be super duper precise or not. So let's try and be moderately precise. So let's see here. So I'm going to. Okay, moderately precise, James. So first of all, I see that my conductivity values, the highest I'm getting is like 12 maybe, and the lowest I'm getting is a little lower than 8. So I at least want to make sure I've got that kind of going on. So I might go up as high as, just for safety's sake, let's go as high as 13, 12, 11, 10, 9, 8, 7, and so on. Okay, and my x values start at negative 36, and then negative 34, 32, 30, 28, 26. Okay, so I'm going to try and just hit the highlights. So if I look at my thing here, I can see that at negative 36, I'm getting a value a little bigger than 10.5. Oops, you can't see that. I can see, you can't see. At negative 36, my value is a little bit higher than negative or positive 10.5. So I'm going to be a little higher than 10.5, maybe right there. And then I'm just going to kind of look at each of the values. So negative 34, I can see that my value is almost right at 8.5. And negative 32, my value's at right about 8. Negative 30, my value's between 8.5, sorry, between 9 and 9.5. At negative 28, my value is between 10 and 10.5. And at negative 26, my value is a little bigger than 11. So that's kind of what it looks like. I've probably gone that looking a little too straight for my taste, but it kind of does this. Kind of like that. So that's what our conductivity values versus our x values look like. And you can see, right, it's steeper over here because we're crossing lines faster over here, whereas it's kind of more gradual in the middle here because there's a lot of distance between each of our level curves over here. Kind of cool. But really the thing I did that made it, to me at least, manageable was to really kind of just take each of these given values of x and find the corresponding points, aka values, on this line here. And then kind of plotted those points and tried to draw the curve that smoothly-ish went between them. Okay, let's ask ourselves the other question, which I didn't actually do yet. So let's say we wanted to fix now x equal to negative 29. Paper, sorry, I got stuff all over the place here. So now, same idea. Oops, come on, papers. Now we're going to fix x equal to negative 29 and plot conductivity versus y. So same idea. We're taking our curve and we're fixing x at, what did I say? Negative 29. So let's do this again. Sorry, we got too many papers. Happens. So let's see, negative 29 is over here. I'm just going to look along this. Sure, along that. And so I'm going to look at the corresponding y values. So here, and here, here, there, there, and there. Okay, so let's try to see if we can graph this. Yeah, sorry, and it's kind of all over the place here. So here's what I'm doing. I'm going to say I've got conductivity on my vertical axis and y on my horizontal axis. And let's see, so we're starting with y values that are negative 33 going up to negative 23. So let's go ahead and do that. So negative 33, 31, 29. And again, your graphs probably don't need to be quite so precise. I mean, they could be, but they're just trying to get a good idea of what this looks like. So if I was going to kind of freehand this without like doing all these points, I would be saying, well, let's see. I'm starting at a y value of a little bit less than 11. So I'm getting bigger. I'm plateauing. I'm going back towards 11, smaller than 11, smaller than 10.5, smaller than 10, hitting 9.5 and kind of staying at 9.5 for a good chunk here, right? It kind of just flattens out completely at 9.5 because you're on that. Oh, you can't see the sign. Flattens out to 9.5 here. And then after this here, we kind of, again, we actually start getting bigger back towards 10 and a little larger than 10. So that's how I kind of, if I was going to freehand it, but I'm not good at freehanding it. So let's just try and do the things. So let's see. Here, my y value, sorry, my conductivity value is a little less than 11 because I'm between 11 and 10.5. So let's start it a little. Let's also give ourselves some values here. So 11, 10. I think we need to go down to 8, but we could. So starting at a little less than 11. Sorry, I know it's hard to see all the things. I apologize. So let's first spot a little less than 11. Right there. And then at negative 31, we are above 11, but definitely not above 11.5. Because, right, if we were above 11.5, we would have hit there would have been another level curve that would hit. So we're a little bit above 11, but not quite 11.5. And then we're going to go back below 11. So the next kind of value at negative 29 is going to be between 11 and 10.5. There-ish. And then going to the next one, we're between 10 and 9.5. And then for the next one, we are firmly at 9.5, I would say. And so from here to here, oops, sorry, from here to here, it's very kind of flat, which makes sense. We're just going to like that. And then from here to there, you're creeping back up towards 10. So I would say this looks kind of like this. That's what this journey looks like as far as conductivity. We started out here, we increased a little, we topped out, we decreased a little, we went down, we kind of flattened out at 9.5, and then we came back up a little. Okay, see, what's up? Yep. Oh. Well. The questions about any of this, what we've done here. Cool. I mean, so level curves, I think are neat. Oh, thanks. Appreciate it very much. Work, yeah, and I really should just emphasize here, right? When we're crossing level curves, if the values are getting bigger, the function's increasing. We're crossing level curves and the values are getting smaller, the function's decreasing. what we're going to see shortly is that we start talking about taking the derivative of your function of two variables. So in fact, what I should really I might as well. So what I would say here is, for example, at this point, if we move in the y direction, is the function increasing or decreasing? Decreasing, or as I should say, is the conductivity increasing or decreasing? It's definitely decreasing. So I would say is at this point, right there, the derivative in the y direction is negative. So if this level curve here, if this represents my function of x and y, then what I would say here is that the partial derivative of my function with respect to y at that point is negative, because the function is decreasing in that direction. Or I should say that a little better. I should say that when we move in that direction, what direction? The y direction, the function is decreasing. So let me ask you all, on this graph, what direction is the y direction? I know it kind of sounds like a dumb question. Right, it is north. It is not north-south, it is specifically north. So going up is the y, or I should say the positive y direction, whereas going south would be the negative y, or the opposite of the y direction. So if I said what direction is the x direction, which way is it? Right, or right, but yes, it's east on this map, or generally, if you're looking at the usual kind of XY coordinate system, it is to the right. So if I looked at this point, and I don't love that point, let's go a little lower. Let's look at that point right there. If I looked at that point, and I said I was going to move to the right, at least in the immediate vicinity, if I move to the right, is the function increasing or decreasing? It is increasing because I'm moving towards a higher level curve, right? At this point here, my value of my function is somewhere between 10.5 and 11. And I'm moving, so I'm smaller than 11. I'm definitely moving towards 11, which means the values are getting bigger. So here, I would say at that point, the partial derivative with respect to x, which is again, really just asking how the function is changing as x is changing, while the function is increasing as x is changing. So we would say the partial derivative is positive because that change is positive, it's increasing. Question.
What is partial derivative?
Right. So that's where we're going. Where I'm probably not going to get today, but what I'm trying to prepare you for when your professor talks about it in the future. So all the partial derivative is exactly the words I'm saying. So when I look at a function, a surface, a function of two variables, the partial derivative of a function with respect to a particular variable is saying, what happens when we move in this direction and not in any other direction? So yeah, I feel like that's where we should go. So let's look at a more concrete example. I know you're not there. I assume you haven't talked about partial derivatives in your class yet.
We did.
You did? Okay. All right. So great. Then we are perfectly in the spot for me to talk about it. It's a great lead in here. So I'm going to go back to my favorite function of two variables because it's easy for me to draw. I'm going to look at f of x comma y equals 9 minus x squared minus y squared. Because I'm good at drawing it, to be perfectly honest. It looks vaguely like this. Yeah, sure. Kind of want to be super precise about it. So let's draw the thing. And it keeps going, right? Let's just stop there. Okay. And that point is the point 0, 3, 0. That point's the point 0, negative 3, 0. That's point 0, 0, 9. That's the point 3, 0, 0. I don't really want to label it. Those are the points I want to label for now. No, it's not the rest. Better. Okay. So here's my surface that looks like an upside down bowl. Or at least a bowl that's not, I mean, I guess that could be a right side up bowl, but it's not a very useful right side up bowl with right side up. But it's definitely right hollow, right? There's no like, it's not a solid, it is just the bowl is the surface. And the question I want to ask is, so at the point, my favorite point on this graph, 1, 2, 4. By plugging in 1 for x and 2 for y, I get 4 for the output, which I'm thinking of as my z. What is the, I'm going to ask it this way, slope of the tangent line in the x direction? Okay, well, let's look at that point. We need some more pens here. I should draw this on the x-axis. So I go to the point 1, 2, 4. 1 in the x direction, 2 in the y direction, 4 in the z direction, which is about right there. So on the level curve, z or c, whatever you want to call it, equals. We've got 1 towards you, 2 to the right, and 4 up. Boom, boom, boom. All right. So at that point, what's the slope of the tangent line in the x direction? Okay, so if I'm right here on my mountain, on my upside down bowl, well, let me ask you all, and I know it's not maybe, so let me ask you a different question first of all. Which direction is the y direction? Is it left, right, up, down, towards you, or away from you? To the right. Right. Okay. Which way is the x direction? It's like that. It's like pointing at you. So that's the problem with drawing 3 dimensions on the 2-dimensional paper, right? It's not perfect, but the usually the x dimension is drawn as the one that is pointing out towards you, and its negative direction is pointing away from you. So the x direction is the one that's coming out at you. Perfect time. So if I'm here at this point that is on the forward side of this mountain, and I walk, and I'm literally up here this high, right? I've gone 1 forward, 2 over, 4 up, and I start walking towards you on that mountain. Am I going to be walking downwards or upwards? Well, let's take a look. So if I'm right here and I slice this with the plane y equal to 2, I get something that looks kind of like this to the clock. Okay. I have to be kind of precise here. My slice there is hard to see. My slice there is parabolic, which makes sense, right? If I think about being on the plane, y equals 2. Well, let's just set y equal to 2. If we set y equal to 2, we end up getting f of x comma 2 is 9 minus x squared minus 2 squared, which is just 5 minus x squared. That's a downward opening parabola. Right? It looks like this. Where that point there is x is 0 and z is 5. And this point here is the point x is 0 and y is 2 and z is 5. And I'm definitely on the towards you side of it, not the away from you side of it. So if I'm right here and I'm traveling towards you, am I traveling up the mountain or down the mountain? Traveling down the mountain. So I'm expecting the slope of my tangent line. This is where, okay, my drawing skills might fall apart here. Expecting the slope of my tangent line to be negative. Now, you might argue, well, James, how do you know that depending on your perspective, that line might have a positive. Do you have a positive slope? Right? If you're drawing things in three-dimensional space, it can kind of be a little like, well, if you turn it around, it looks like it has a positive slope. And I would agree, right? If I walk backwards, I would certainly be having a positive slope. But the point here is that when we're moving in the x direction, we are specifically moving in the positive x direction. So I'm asking if I move in the towards you direction, oh, my function values are really small. Now that's a lot of talking to get at the point which is not too hard to find, which is that if I take my function here and set y to be a constant, what's the derivative of this with respect to x? Well, if I take my partial derivative of this function with respect to x, I'm going to get negative 2x. I'm just using my regular derivative rules. Now I'm going to back it up a little bit to be a little more general. But if we're thinking about y being 2, right, because we're literally at this point, we're saying if I'm only moving in the x direction, oh, this is what I want to think. If I'm only moving in the x direction, y isn't changing. I'm not moving left or right. I'm only moving forwards or backwards. So y, for all intents and purposes, is a constant. Specifically at this point, or on this plane, y is 2. I literally plugged it in and said, oh, I've got 5 minus x squared, the derivative is negative 2x. And then I will also point out the derivative of that function evaluated at the point we're interested in, which is the point 1, 2, 4. Well, what am I going to plug in for x? Sorry, I can't see it. Sorry, let me zoom back out a little bit. If I'm trying to find the derivative and my derivative is negative 2x at the point 1, 2, 4, what am I plugging in for x? 1, 2, or 4? 1, right? The x coordinate. So my slope at that point in the x direction is negative 2. And that's, at least in this example, what the partial derivative of x is at that point. I will say that if we don't actually set y equal to 2, if we go over here and we say, oh, our function is 9 minus x squared minus y squared, and I want to find the partial derivative of x just in general, the idea is we pretend y is a constant. Or really, I should say, we pretend that anything that isn't x is a constant. So if I'm taking the partial derivative of the function with respect to x, I'm saying, what happens to the function when I move in the x direction and not in any other direction? I'm not moving in the y direction. I'm not moving slightly to the left or slightly to the right. Right? I'm only moving forward. So we're asking, oh, well, if I'm only moving forward, y is a constant. And what's the derivative of a constant? Right. So when I take the derivative of this with respect to x and pretend y is a constant, my derivative is going to be 0 minus 2x minus 0. Yeah.
Is that the same thing as saying y is fixed?
Yes, y is a constant, the same as saying y is fixed. Exactly. 100%. And just to look at the other way, if I wanted to instead find the partial derivative with respect to y, now I'm pretending x is a constant. So I'm moving in the y direction and not in any other direction. So that's going to be 0 minus 2y. A quick note on notation here. Those are not d's, those are del's. They are curly d's. So I know it's kind of dumb, but someone's going to write this. Someone's going to write this then that means the derivative. Whereas someone's going to write this, and that's going to mean is the partial derivative. Sometimes people are very loose with this. People are not careful at all with this. Really, what you have to do is you have to pay attention to the context. If your function is a function of more than one variable, like if I had, for example, f of x comma y equals to x cubed minus y squared, I can't find the derivative with respect to x. Not a thing. I can only find the partial derivative because it's a function of more than one variable. If you have a function of more than one variable, you can't just find its straight up derivative. You have to find. But yeah, people, hopefully professors do a good job with the notation, but if they're not, it's kind of, it looks like a D, it's kind of like a D. We just use a curly D because it's something slightly different. Oh, I know what I was going to say. So at this point here, if we instead want to find the partial derivative or the slope of the tangent line in the y direction, so if instead of moving towards you from this point, if I move to the right, I'm still going down the mountain. But my slope might be different. So what I'm going to do is I'm going to say, well, I'm going to run out of paper. What I'm going to do. I guess I'm going to write on the paper here. So at that point over there, at the point 1, 2, 4. So now if I hold x as 1, my function of 1, y is going to be 9 minus 1 squared minus y squared, which is 8 minus y squared. If I want to find the partial derivative, del f del y, well, we already found it. We know it's negative 2y. And if I want to find the partial derivative at that particular point, which is the point 1, 2, 4, I'm going to plug in what? So it's a little bit steeper of a negative slope there because I'm a little bit further down the parabola because the cross-sectional parabola there is a higher one. So I'm going to try and draw it. This might be really actually where my picture really does start to fall apart. If I try to draw it here, here's what it kind of looks like. Wow. Oh, come on, James, you can do it. Maybe, I don't know. Yeah, I kind of trashed it there. Sorry. Supposed to look good and it doesn't. Okay, maybe that's what it looks like, more like that. But if we look at this point here, and we're looking at the slope of the tangent line in that direction, it is a steeper negative slope. Again, not super easy to see because we've got things going on in 3 dimensions and it's kind of hard to see, but I think maybe pretend like that's the right idea. Yeah. No, not at all.
Like if you're moving up or down, you're not doing either you're like left and right, or
So sorry, say that one more time.
so I just like what is like the if you're in the x direction, like
If we're moving in the x direction?
yeah.
Okay.
It's like not like up or down.
Well, so here's what I would say. When we talk about moving in the x direction versus the not, we're kind of thinking about living in 2 dimensions. So the third dimension, the z dimension, the vertical dimension, is not really in play. I'm thinking level curves. I'm thinking that if I'm standing right here and I move in the x, oh no, yeah. Sorry, I've got a better picture for this. That first picture I was using. Oh, it's so all over the place. Where'd you go? Better picture that I really would like to have right this moment to look at. Oh, there it is, right there. Cool. Yeah, cool. Okay, so the whole idea is that, like, right, is that if I am sitting closer, let's cool. So if and let's pretend that, like, so let's say this is the so I know this is kind of backwards. Let's say this is the positive x direction, and this is the positive y direction. So if I start maybe say at, okay, we're going to try. If I start at this point here and I move in the x direction, well, am I going to be increasing or decreasing? Increasing, right? My level curve values are higher, right? And if I project up to the map, if I start right here and I move in the x direction, I am moving in that direction in towards the mountain, but the mountain's in the way, so I end up going up the mountain like that. So that's kind of the idea, is that if I'm moving in the kind of flat plane in either the x or the y direction, whichever point I'm pointing on, the x or the y direction, right? The question's asking what's happening to the height function z values as we move either towards you in the x direction or to the right in the y direction. So here I would say that as I move in this x direction, I would say, well, here the partial derivative of my function with respect to x is definitely positive because the function is increasing as I move in that direction. The function is increasing. Whereas if I moved in the y direction, it would be kind of boring. It'd be kind of flat. It looks like at that point, the partial derivative with respect to y is probably like 0. Because I'm not really increasing or decreasing as I move in the y direction. Good question. Thank you. Excellent. Let's see, what else? Sorry, my pictures are all over the place. I'm trying to keep things in some order, so they will eventually post this note. Cool. Just want to make sure that things are not totally all over the place. Right. Okay. So generally, if you're trying to find a partial derivative, you're trying to find out about how the function. In fact, I should just say, if you're trying to find a derivative at all, right? A derivative is just asking how is this thing changes as this other thing is changing, right? Derivatives are rates of change. They're saying how does one thing behave as another thing behave? How does one thing change as another thing? How does y change as x changes? That's why when you talk about like regular functions back in 17a, the derivative is really the slope of the tangent line, because you're asking how is y changing divided by how is x changing? Oh, that's just the change in y over the change in x, which is the slope of the line. So we can then kind of move forward a little and be like, well, we can apply this more generally, right? We don't have to be able to actually look at the graph, although it's nice, right? Graphs are great, but we could say like, what if my function, for example, was, I don't know, x cubed times y squared plus x to the 5th minus 4 sine of y. And I wanted to know just in general, what are my partial derivatives? What is the partial derivative with respect to x? And I should point out, this is common notation, but this is also common notation. Sometimes people write it as del f del x. Sometimes people write it as f sub x. Those are the two pretty standard notations for the partial derivative with respect to x. Black pens are not doing any favors here, so we just blue pen instead. So, well, I'm going to treat y like a constant. So if I'm looking at x cubed times y squared, what I'm really seeing is x cubed times 5, or x cubed times 6, or pick your favorite number, but it is just acting like a regular constant number. So I'm going to take the derivative. I'm going to get del f del x. Well, the derivative of x cubed is 3x squared, and the constant multiple just hangs out. Because constant multiples hang out, or you continue to multiply them. Similarly, the derivative of x to the 5th is just 5x to the 4th. But for sine of y, there are no x's there. And so the derivative of 4 sine of y, well, that thing is a constant as far as x is concerned. So its derivative is, which we don't need to write, but I want to write to be emphatic about it. So we get 3x squared y squared plus 5x to the 5th. On the other side of things, the partial derivative of this function with respect to y, well, we're going to do the same sort of deal, but now we're going to treat x like a constant. So x cubed is constant, y squared is y squared. And I know the derivative of y squared is 2y. So I know the derivative of x cubed times y squared is x cubed times 2y. And the derivative of x to the fifth, well, I don't see any of my variables there. Its derivative has got to be 0. And the derivative of 4 sine of y, well, so I want to point out, just like for y squared here, this constant hung out, right? X cubed just stuck around. For sine of y, this constant's just going to hang out. The multiple of 4 is hanging out, the multiple of x cubed is hanging out. They're both constants in the eyes of y. And then the derivative of sine of y, and I would then rewrite this as 2x cubed y minus 4. That would be the partial derivative of that with respect to y. And then, of course, you can do higher partial derivatives. So you can do the second partial with respect to x, you can do the partial derivative with respect to x again, or y again, or the mixed partial. So there are other things we can do, and we'll talk about those.